So, do you guys have any questions about CPV and the systems in general before I get into the physics? Go ahead. It's either glass or plastic, so PMMA is often used for the Fresnel lens, or silicone on glass. You take a piece of glass and you have basically silicone, which is a rubber, create the notches to give you the Fresnel lens effect. No, all that stuff has been worked out. So PMMA, so on your headlights on your car, the plastic is made from PMMA. And so the automobile industry had to get through all these issues that you're referring to, where I think automobiles a long time ago, they used to yellow. The headlights used to yellow over time. So they have now gotten rid of the compounds within the PMMA that yellow. Same thing with SOG and whatnot. So a lot of these materials issues have been solved to give you 30-year reliability. So I'm going to go through now the physics of these solar cells. Yeah, so I'm now going to go through the physics of these solar cells, and there's a lot of slides here. I'm going to skip a lot of the things that I think you guys are aware of and really just try to point out the things that are different about CPV or multijunction, the cells in CPV, the multijunction solar cells. So you guys are familiar with thermalization loss. When you have a single junction compound semiconductor, you lose a lot of the energy between the energy of the photon and the band gap of the semiconductor that is being used to collect and deliver the power. As you know, in a single junction solar cell, if you use a narrow band gap semiconductor, you can absorb a large portion of the solar spectrum. However, you'll be delivering that current at a low voltage. Conversely, you can increase the band gap of that semiconductor, deliver a lower amount of current, but at a higher voltage. This then gives you, as you guys are very familiar with, the traditional trade-off between efficiency and band gap. For a single junction solar cell, the optimal band gap is about 1.4 electron volts, and as you heard from Eli Yablanovic a few weeks ago, Alta Devices, his company that he started a few years ago, now has single junction gallium arsenide solar cells operating around 30% efficiency. However, to go higher in efficiency, you really need to move to a multi-junction solar cell. And the way you do this is you stack different materials on top of each other, with each material tuned to absorb a different part of the solar spectrum. So here in this case, if you look at over on the right-hand side, the blue material is going to have a higher band gap material, and it's going to be tuned to absorb the UV and a portion of the visible part of the solar spectrum. The green material is going to be used to absorb kind of the middle part of that solar spectrum, and the red material is going to have the lowest energy band gap and will be used to collect a portion of the infrared. This allows you then to minimize your thermalization loss as you transverse the solar spectrum. Theoretical efficiencies of these multi-junction solar cells under concentration can be really, really high. Now here are two different studies, one done by NREL and one done by the Fraunhofer Institute in Germany, showing under concentration, as you increase the number of junctions within a multi-junction solar cell, theoretically you could get above 60% to maybe even 70% efficiency. Now practically, when you look at a number of issues, you can get about 80 to maybe 85% of these theoretical predictions. So what this means is, going into the future, efficiencies of 50 to 55% under concentration should be possible. And the exciting thing about that is the market in which CPV will then be able to address, or I should say the opportunity, will be much wider than it is even today. So one of the challenges of multi-junction solar cells is integrating these different materials in your solar cell stack. So what is being done today? So if you look at the periodic table of elements, then you look at band gap energies versus lattice constant, one of the really nice things you have available to you are three different compound semiconductors that are lattice matched. And so lattice matching, as you know, or I should say the lattice constant, is the atomic spacing in a material. And if you can find different materials which have the same lattice constant, you can very conveniently epitaxy grow them on top of each other. Now what's been done today, is people have made triple junction solar cells using germanium as the bottom junction, gallium arsenide as the middle junction, and indium gallium phosphide as the top junction. These materials are lattice matte, so that's that green line. And that's a very convenient way in which you can integrate these materials together on top of each other. Now, what do these solar cells look like? As you guys learned on Monday, these are, I should say, the most common architecture is to series interconnect these solar cells via tunnel diodes. So there are tunnel junctions in between each of these different diodes. Each junction is an N-on-P solar cell. It has all of the components found in a traditional cell, but for each junction. What I mean is there's a window layer, there's an emitter, there's a base, there's a back surface field, and you have to do that for each of the individual junctions. Now, because you're using different materials for each of the junctions, it's quite a challenge because now you have to optimize not just one set of materials, but in this case, 3 different set of materials. So it's really like optimizing 3 different solar cells in one. The voltage out of the device is the sum of the voltages developed across each junction, and the current out of the device is given by the junction which produces the least amount of current. So again, because these diodes are connected in series, the current out of the device is limited by the junction which is producing the least amount of current. So interestingly, when you're using these cells, at a given part of the day, the solar spectrum is changing. There will be one junction which is producing the least amount of current, and that's going to determine the current coming out of your cell. So one of the interesting things you can do with a multi-junction solar cell is optimize its band gap for energy yield. So rather than efficiency, you know that there's going to be a changing junction which is going to be limiting the current throughout the day. And so rather than optimizing for efficiency, which you may do in a single junction solar cell, optimizing for energy yield makes a lot more sense in a multi-junction solar cell. So just a little bit of a preview of what these different material stacks look like and what the efficiencies you can get. And again, if you look at, you can get about 80% of what these theoretical efficiencies tell you, and I'll go through in detail what all these different technologies are. So skip ahead here. I think you might have even had this exact slide. So what I wanted to just point out here was these solar cells are pretty complicated. They have about 15 to 25 layers within them. The layer thicknesses range between 5 to 10 nanometers and a few microns. Typically, these solar cells are grown using either MOCVD or MBE. And the architecture that's being used today are N-on-P diodes with a top grid electrode, a top AR coating. So unlike silicon solar cells where you can move to a backside contact architecture, because of the way we interconnect these solar cells, you necessarily have to have a top grid line architecture. And as you can imagine, this is a very simple circuit model of these solar cells. And what you'll see under concentration, as this is actually real data that we took in my lab, as you increase in concentration, your current will go up linearly with concentration. So if you go from 1 sun to 1,000 suns, you will get 1,000 times more current. That doesn't do anything for you in terms of efficiency. But the real key here that's interesting is your voltage actually goes up with concentration. So as you put more light onto your solar cell, your quasi-Fermi levels actually get driven towards the band gap, and that means the voltage produced out of each junction increases, and this is why the efficiency increases under concentration. And that's something that's very different compared to a regular PV cell operating at 1 sun. I'm not going to spend a lot of time talking about minority carrier recombination. The one thing I will say is that because we deal primarily with direct bandgap semiconductors, OJ recombination isn't something that we typically care about. Radiative recombination is the fundamental limiting factor here in multi-junction solar cells. However, practically, what you're concerned about is bulk Shockley-Reed-Hall recombination as well as interface recombination at your front surface field and back surface field of your solar cell. And that's frankly where I spend almost all of my time being concerned about in trying to develop a higher efficiency cell. So talk a little bit about maximizing efficiency, this is going to be pretty straightforward for you guys. AR coatings, because we're trying to absorb light from about 350 nanometers out to 1800 nanometers, multi-junction solar cells typically have much more sophisticated AR coatings. And here I'll give you an example of an AR coating which stays relatively low in reflectivity. I haven't shown it all the way out to 1800, but these are typically multi-layer AR coatings. Now I'll talk a little bit about getting current out of solar cells. This is just a schematic of one junction. In a multi-junction solar cell, you would have these stacked on top of each other. The structure is very similar as you would see in any other heterojunction solar cell. You have an AR coating, a window, an emitter, depletion region, a base, and a back surface field. This is very familiar to you guys. And then I've written out the current equations based on the well-known quantum efficiency equations. You guys know all of this, but the one key thing I wanted to point out is these analytical equations are very, very accurate. So oftentimes when we study things like transistors and whatnot, we need to use a much more complicated simulation tool that will solve a Schrodinger-Poisson equation, look at heterostructure offsets and things like that, as you would study in 216 or 316. So one of the things that really struck me when we started to work on these solar cells are simple analytical models work. So these equations, I play with them all day, every day. I can model exactly what's going on in my solar cells, and it makes it very, very convenient. So I thought you'd just find that a little bit interesting. These quantum efficiency curves look very similar to any traditional solar cell. And as I mentioned a moment ago, the things that we care about and the things that are practically engineered on a daily basis are really things like surface recombination velocity at your window or your back surface field. And these plots just give you an idea of how your quantum efficiency can degrade depending on how those recombination velocities change. This is actually some data from my lab showing a real quantum efficiency curve. If you integrate each of these individual junctions, you get somewhere around 14 milliamps per square centimeter. Now, interestingly, this bottom junction has a band gap which is much wider than it needs to be. It produces about twice as much current as each of the top two junctions. And this is actually measured data. So the way you do quantum efficiency, I actually don't have this in this presentation, but the way you measure quantum efficiency in a multi-junction solar cell is you have to light bias the cells, the junctions that you don't want to measure. So for example, if you want to measure the quantum efficiency of the top junction, you put a very weak chopped beam on the top junction, and then you flood the other junctions using LEDs or lasers so that they're producing more current. So in a quantum efficiency measurement, the junction which is producing the least amount of current gives you your signal. And so you just have to do some light biasing. So that's actually how we make these measurements. So this is just to give you an idea of what these QE curves look like. And what we do is we integrate these and we can understand how much current each junction is going to be producing. And then by looking at these QE curves and integrating them with a variety of different spectra, we can actually predict energy yield out of these solar cells. Let me then move to the open circuit voltage. You've got the traditional dark current equations. There's nothing different here other than you have to optimize them, optimize your dark current for each of your individual junctions. Now, this is the key point. I mentioned this earlier. If you look at efficiency, VOC, and fill factor versus concentration, one of the remarkable things that you'll find is that your VOC at 1 sun in this particular solar cell is 2.6 volts, and at 1,000 suns, it's 3.25 volts. That's a 25% increase in voltage. Your current goes up linearly. And that's why at 1 sun, the efficiency of these solar cells is relatively low. In this case, it looks like it's 26%. Do I get that right? No. At 1 sun, it's about in the low 30s, and under concentration, it's over 40%. Now, what you'll notice here is if you look at efficiency versus concentration, that efficiency increases, so it tracks your VOC, but eventually that efficiency rolls off. And that's because of series resistance losses within your solar cell. And I'll talk about that here in a moment. Your VOC, typically what you want to do is make your junction as thin as possible. You want to absorb as much light. And again, your VOC is very sensitive to recombination. And this gives you an idea, is as you make your solar cell thinner, you can either get a higher VOC, which is what will happen if you have very good interfaces and very good materials, or it can actually get worse if you're going to be very sensitive to the recombination velocity at your front. Now, one of the things I wanted to point out for VOC is that your VOC at 1 sun is a very good proxy for how good your material quality is. This was a plot published by Richard King at Spectralab back in 2010, and he's a big proponent of using your band gap minus your open circuit voltage as a metric for how good your material is. And so what he plotted was, if you look at the blue curve, which is your measured band gap, your measured VOC, that's your band gap versus different materials. And then in green, your VOC versus your different band gaps, your different materials. What you'll find is the best materials have a EG minus VOC of about 400 millivolts. In the Alta Devices configuration, because they have a back reflector, you can actually get that down to 300 millivolts. So one of the things we do at Solar Junction when we're developing a new material or a new band gap is we measure single junction solar cells with that material at 1 sun. And we know that if we're not down close to about 400 millivolts, that material is not going to be suitable for integration into a multi-junction solar cell. So this was a very nice study done showing for different materials that there's this very good convergence of about a delta of about 400 millivolts. Now let me talk about fill factor. You guys are very familiar with fill factor. One of the things that's really critical in multi-junction solar cells under high concentration is the resistance within the solar cell. And so a lumped electrical model like what's shown in the upper left is really inadequate to predict the power out of a multi-junction solar cell under concentration. And one of the reasons why is you have distributed resistance within your solar cell. And so this is a cartoon. It might be a little bit difficult to understand, but in between your grid lines within a solar cell, you have a varying degree of current that's traveling within the emitter of that topmost junction. And that resistance, as well as the resistance of the grid line that's carrying that current to the external part of the solar cell, gives you resistance which you have to care about and engineer. Different parts of in a CPV multi-junction solar cell, under concentration, different parts of your solar cell will be biased differently due to the distributed resistance within your solar cell. And one of the things I did here was I'm just pointing out the different losses, different resistance losses as well as shadowing loss within a solar cell. And so one of the things you have is, if you look at just the topmost few layers of your solar cell, you have current that's coming up through the solar cell. It's then traveling laterally within your emitter, being collected by your grid line, and then traveling down that grid line to your bus bar so that it can be collected externally. These different resistance components are important. And when you look at adding these different components together, this black line is your shadowing loss. As you get to smaller grid spacing, you have more shadowing within your solar cell. And then the blue line is your contact resistance, your orange is your emitter resistance, and the green is your grid line electrical resistance. If you sum all of these together for a particular concentration, you'll find there's an optimal grid line spacing when you design your solar cells of about 100 microns. So most CPV multi-junction solar cells have a grid spacing that is much narrower than what you'll find in a traditional flat plate solar cell. This is just another plot of the different power loss contributions. And I think I'm just going to skip this here. This is just a little bit of an overview of some different grid lines that people have implemented in CPV multi-junction solar cells. You guys learned about tunnel junctions. These are very thin, highly doped N-on-P diodes. that are inserted in between the individual junctions. What's interesting is that under this peak current density, some people call it the Esaki peak, it's very, very important. That peak needs to be larger than your short circuit current within your solar cell. Now, these tunnel diodes are very difficult to grow. They're actually a big problem, and what people found in the industry early on is when there was still a lot of engineering development needed to make tunnel diodes, is if your Esaki peak, the tunneling peak current density, is lower than your short circuit current, when you trace an IV curve outside, you end up getting this kink in your IV curve. We've actually made bad tunnel diodes which show this. If this ever happens in the field under real operation, you can imagine what your fill factor is. In this case, it's like 40% or something like that. So the amount of power out of your solar cell is rapidly degraded. These days, however, people have made tunnel junctions that have peak tunneling current densities that are much, much higher.